The construction industry is evolving, and mass timber is at the center of a major shift. In this first of a two-part series, we explore how this innovative material is changing the way we build, offering sustainability, strength, and new opportunities for the future of construction. From reducing carbon footprints to streamlining projects, mass timber is more than just an alternative. It's a revolution. Sit back, settle in. Welcome to Shift.
All right, my guests today are Brent Olund, founder of GreenCore Structures, and Wayne Klaczek from C-FER Technologies. Gentlemen, welcome.
Hi. Great being here. Thanks so much.
It's nice to have you both here. And, I was having some conversation with a colleague about this work that's going on with GreenCore and C-FER, and it's pretty cool. And I'll also admit I was there for a tour, and I saw that giant press that was used to test the technologies, or Brent's technology, but we'll get into that in a bit because I found that utterly fascinating. But let's start right from the beginning and give our listeners an introduction to mass timber technology. So Brent, we'll start with you. What is mass timber technology?
Well, mass timber is large engineered wood elements that are created by gluing together many pieces that came from many different trees. Traditional construction of wood frame or stick frame, typically housing construction, uses individual boards that each came out of one tree, but mass timber is much larger elements laminated or glued together with plies or smaller pieces to make large elements of wood.
And does that make it structurally stronger?
Absolutely, because wood has kind of a system factor. A single board might have a knot or defect in it, but by the time you glue them all together, you make something of very uniform properties from one element to the next.
Now, how big are these pieces of wood, these laminated boards? How big are we talking?
Well, the largest that I've heard of is 12 feet by 60 feet by a foot thick. But they vary. I mean, they're as big as you want to buy a press to make them. Then the challenge becomes highway trucking. If it's over 10 feet wide on your truck, then it causes some issues with trucking. So really the limitation of the technology is the size of our roads, actually.
So what inspired you and GreenCore to develop this technology?
So I had the fortune of being chosen as a construction planner and later construction manager and overseeing the construction for the 18-story wooden tower Brock Commons Tallwood House at the University of BC. And one of the things that I learned there was that the concrete cores would have to be done out in front of the wood construction because they were taking up too much crane time and because of occupational health and safety restrictions on other work to happen below the forming operations for freestanding concrete cores, which are the most common type of lateral support system for mass timber buildings. And so what I wanted to do was come up with a much faster system. You can imagine waiting for concrete to cure, and every story of a concrete core might take up to a week of time. We don't have that much time when the rest of the building in mass timber could have proceeded 2 floors per week. There was basically a schedule mismatch between the available structural systems for building cores and the otherwise feasible, very fast pace for mass timber buildings, including their structure and their building envelope.
Do me a favor and define core for the audience.
So the core is usually the part that the stairways or elevator are in. And it's a tubular element of concrete up through the entirety of the building. And in mass timber buildings, that is normally built of concrete, and it's resisting the entire horizontal loads on the building, whether that's wind loads or seismic loads.
I see. Okay. But in these mass timber buildings, will they still be made of concrete, or is it now mass timber?
I would say we're the first ones to try to make wooden cores for buildings over 10 stories.
I get you. Okay. So it's the floors, the cores, the whole 9 yards.
Yeah, I mean, there's even with a mass timber building, you have to have the building envelope, like the windows and such, to keep pace with the structure, so that you're not exposing the structure to rain for any significant period of time. So that the structure and the building envelope have to go up very quickly. And what we're trying to do is have a core system that can also proceed at the same pace, so it doesn't hold up the rest of the building, or worse even yet, have the entire rest of the building have to wait until the core is done.
Right. Okay. And so far as you know, you guys are one of the first to be doing this.
We will be the first panelized but seismically competent core system.
Right. Yeah, no kidding. So now the advantage here is, but you can put up buildings faster because of that.
Absolutely. I mean, in Brock Commons, we did Brock Commons Tallwood House. We put up the building at a pace of 2 floors per week from June 10th to August 9th of 2016. This is 8.5 years ago now. But we put it up at a pace of 2 floors a week, including the structure and the building envelope, but not including the cores, because they had to be built out in advance. And when the cores have to be built out in advance, it means that the entire timeline of the core has added that much time to the project schedule and affected the end date of the project by that much.
Okay.
And so what we're trying to do is shorten that in terms of its requirement of time per floor, and especially crane time.
Sorry, if I can take that for a second, John. Maybe just building on what Brent said, I'll highlight that the Brock Commons Tallwood project that Brent worked on is really a showcase, I think, for the Canadian industry. So at the time it was built in 2017, it's the tallest lumber building in the world. Is that right, Brent?
Yeah, for a period of about 2 years, and then one in Vienna topped it after that, and then one in Norway, and then one in Wisconsin, which is currently the tallest.
Yeah. So, I mean, it really, I think Canada had a great role, and Brent in particular, in like highlighting the capabilities of this technology. So, great opportunity for us.
Here, I want to understand quickly, a large scale building, I think you said earlier, normally you go up to 8 floors, you're looking at 10 to 18.
Yeah, that's right. Buildings normally let's say over 60,000 square feet is kind of where our technology intends to start with, and above 8 floors.
Okay. Now, when we think about mass timber, how is that contributing to sustainability and environment?
Yeah, actually, so what mass timber is doing is 2 things in terms of its environmental benefit of the material itself. The material is sourced from smaller and more rapidly growing trees because they're all being glued together. The individual pieces don't have to be as large. So the forest matures faster and earlier. You're harvesting material from forests which are more rapidly renewable because they don't need to grow for as many years before you can harvest the material. That's the first thing. The second thing is the carbon footprint of the entire process, from logging and trucking and sawmilling and making mass timber elements out of it, and then trucking those, preparing them and bringing them to a job site. The landed carbon footprint of that material is far lower than steel or reinforced concrete. And then the next thing is that carbon is effectively encapsulated into the building for a long duration of time. The buildings are designed to last 75 years or 100 years. And so what is actually happening is that carbon dioxide is being taken out of the atmosphere to grow the trees. Then the trees are being cut and made into mass timber, and the mass timber is being sequestered effectively into the permanent building, so that it's a cycle of taking carbon out of the atmosphere.
I see. Wow. Okay. Elaborate a little bit on what a seismically resilient assembly system that you guys developed at GreenCore. What does this mean? Why should people care? And how is it relevant?
So firstly, the obligation of the building codes is to have, in an earthquake, that the building stays standing and the people get out alive. Unfortunately, how the building code is designed for the most part is with tables of of materials and how much energy is used up when those materials are, bent, torn, crushed, or otherwise stretched or destroyed. So the building code, in terms of seismic, is all around tables of what happens when materials get destroyed. And the effect of that is the design of buildings that are only good for one earthquake. So the building's designed to have you get the people out alive, and afterwards to be effectively garbage that you have to then tear down, and picture the carbon footprint of tearing the building down and having to build an entire new one. That isn't what GreenCore is working on here. What we're working on is a system whereby the ground motions are shared up into the building across multiple levels, but there's some energy absorption and attenuation into the system so that you can think of the building like a tall piece of bamboo, and you're moving the ground under that, and the displacement is shared across different heights of it, but nowhere along does it actually snap or break something. That's more what we're doing. We have in our proprietary and patented fastening system a combination of springs and viscous pads, and the springs serve an important role of storing energy, which is then, when the shaking stops, used to recenter the building back to where it's supposed to be. So we're actually using springs to store energy, and we're using viscous pads to dissipate some energy. Those are both elements of our connection system.
So if I got this right, then people are going to be able, earthquake happens, people are going to be able to get out of the building, and then when the earthquake goes away, they're going to be able to go back into the building.
Yeah, that's right. There will be architectural finishes with damage because, for example, drywall plasterboard is not made to take much, in plane motion before the corner beads are going to snap and other cracks will happen. Cosmetic damage is deemed to be okay because people could still use the building. So we're making buildings that are going to be recentering after the earthquake. And if you picture the most common core system, the concrete core, if you have a horrendous ground shock and it shifts the top of your building quite a bit compared to the base of it, what happens is that in one diagonal, you get a whole bunch of micro cracking of the concrete, and in the opposing diagonal, you get a bunch of stretching of the rebar. That's great at using up energy, but unfortunately what it does is it leaves the core system displaced to wherever the worst earthquake shock has put it over to. And there's no energy left in the system to bring the building back. Right. So what happens then is you have to tear your building down and put a new one. And if you're doing that with concrete, then you're using also a high carbon footprint material in terms of what it takes to demolish it and build a new building as well.
Right. Now, I want to bounce over to Wayne here, because we've talked about stressing these materials, trying to break them, seeing what sort of forces are going to be able to withstand specifically. You're talking about an earthquake. How do you test all of that stuff, Wayne?
That's a great question. So I guess the way you test it is, you use a systematic and rigorous qualification process. The neat thing about it, I guess, from C-FER's perspective, is across different industries, that process really tends to be pretty similar. So we're blessed at C-FER that we do full-scale applied research for aerospace and the nuclear industry and oil and gas, obviously, and mining and the construction industry. And I guess one of the things that I've always felt, that's kind of interesting is all of those industries tend to use the same chain. So they all start off with modeling, advanced modeling, simulation. They always move into small-scale testing. It always moves into full-scale testing at the end. The full-scale testing really is essential to making sure that you check all the boxes and you fully qualify the system. It's really hard to scale things up. So the full-scale testing that Brent and the GreenCore team did was, in my mind, extremely comprehensive. And it's, I guess, designing an experiment that covers all of the conditions and all of the loading that the technology is likely to see is really, really important. Here's the part where I'll, sort of beg ignorance. So I'm a mechanical engineer, but probably the wrong kind. Brent is at a level of structural engineer that far exceeds mine. But thankfully, we've got a lot of really qualified structural engineers on the C-FER team that can speak his language. When it came to quantifying his technology, it was really important that we designed the tests in a way that they were safe and that they were very carefully instrumented and very tightly controlled. And that's also, I think, common to a lot of the full-scale testing we do.
Okay, so now I think I mentioned at the start of the podcast that I had gone to C-FER for a bit of a tour to have a look around, and I saw that massive press. And this press is really something to behold. It's not a handheld press, people. It's a massive, I don't know what footprint it takes up.
It's 3 stories tall, and it's about 12 feet by 10 feet at the footprint of it. And it's actually a tension device as much as it's a press. You can pull materials apart there. So
okay. So you can squish them and pull them apart.
Yeah,
it is something interesting. Like a lot of people, they're surprised, I think, to learn about the capabilities that are in Alberta and Edmonton at C-FER in this, relatively small organization. We really do have global assets. So we're quite blessed to have some of the experimental capabilities that we do in the lab. The press, the hydraulic system that you guys are talking about, that we tested Brent's technology in, is what we call our universal testing system. So it is large. It's, a couple of stories. It's 3.5 million pounds of compression or tension. Most people, have a tough time fathoming sort of what that means, but the space shuttle, when it launches, puts out about 5 million pounds of force and thrust. So if you kind of want to think about the big hydraulic press as, a close to a space shuttle of force, that sort of puts in perspective what, the testing limits of what this technology was put to. I guess at our other facility, we've got presses right now that are the largest in the world. We have a horizontal testing system that was sort of at our lab, John, that's 16 million pounds. So now you're getting into the 3 space shuttles, if we're using that as a unit of reference.
Right.
So we're used to testing things at really, really high loads, extreme conditions, whether it's high temperatures, low temperatures, high pressures, high loads. In Brent's test, it was really important that we were able to get to those high loads, but also in a carefully controlled way. Like cyclic loading was really important. And then high quality instrumentation was really, really important.
So cyclic loading, does that mean you apply pressure and then take the pressure off, apply it again?
Exactly right, John. So you heard Brent talking about the seismic resilience of the technology. So one of the tests was purely focused on evaluating the cyclic loading response of his technology. That's actually something else that's pretty unique when it comes to the big testing systems at C-FER, actually. A lot of the other large frames in and around the world, they can get to high loads, like they can get to 8 million, 10 million pounds, but a lot of them are designed to get there over minutes or even hours. The system that Brent leveraged at C-FER is got a very fast, oversized hydraulic system. So we can do high frequency testing. So go from 0 to high loads repeatedly, quickly. So that was a big benefit. Now, in his case, we ended up going beyond that a little bit and designing a custom system that leveraged our strong floor. So one of the other things that's neat about the C-FER Southside Structural Lab is it's got a massively reinforced concrete core that we sort of call the strong floor, and it's this really versatile structural testing facility. It's about 6.5 feet thick of concrete with big steel post-tension cables and lots of versatility. It's in a lot of ways, it's like a big Lego set that lets you build exactly what you need. So Brent's test leveraged that system, and we built something custom to really make sure that we put his technology through all the paces.
Right. Well, I guess if you want to be earthquake resistant, you got to make sure it's it's gonna perform. So 3.5 million pounds. Brent, maybe you can give us a sense of what sort of forces a building would go through during an earthquake.
Well, I guess just for the listeners, I should clarify that GreenCore and C-FER have done 3 different series of testing together. So the first ones we did were anchored into the strong floor, was a test system to put pure shear into the panels. And effectively what we were testing there was the shear strength of the new wood panel material that we had found in the market. And, we also tested to some extent our connection system within that first test. But the second test was the cyclical test, also anchored into the strong floor. And then the third series of testing we did at C-FER was in that machine that you saw there, the universal testing system with the 3.5 million pound load capacity. What we did there was to perform a tension test that went across our interfaces between our wood and our steel. We have a proprietary connection, not only from steel to steel at wall ends to columns, but also from wood to steel at wall panels to the ends of those walls. All of our mass timber wall elements have steel ends on them. And in the universal testing machine, we tried to pull those apart because we needed to understand the extent of their overstrength. And
right.
we believed that our, say, 10-foot long panel interface would have a yield load of 400,000 pounds and an ultimate load of 560,000. What was tested instead was that the yield load was up at 480,000 pounds. The ultimate load, the highest load we could apply to it, was up at 710,000 pounds. So certainly we weren't breaking a sweat with that equipment, able to go, nearly 5 times the load that we needed for our particular specimen. It just illustrates how capable that large testing equipment is.
Right. Yeah, that's pretty impressive. So now if I understand correctly, and I'm going to use the analogy of a credit card, a little, you got a credit card and we've all had cards where we go, well, I got to turf this card. So we bend it back and forth to break it. So you subjected some of when you were talking about 45 different iterations, is that like bending a credit card?
It's a good analogy, John. I think credit card, just because it's plastic. So this is exactly plastic or elastic deformation. So what these guys are talking about is are you bending this thing far enough that it's going to come back to its natural position or not? And with Brent's technology, I mean, wood is much more forgiving in this sense. It can take that cyclic loading and it's less likely to crack or plastically deform, and
right.
You're not going to break your credit card.
Join us next time on Shift for part 2 of my discussion with Brent Olund from GreenCore Structures and Wayne Klaczek from C-FER Technologies. I'll leave you with a few words from Brent that come up in part 2.
GreenCore exists to improve the availability of housing. That's what our actual purpose is. And in the construction industry, the productivity has been famously poor. Like the actual productivity of construction now is as or worse than it was in 1960.